Mastering algorithm design through practical applications in Python. In today's data-driven world, algorithms form the backbone of every technological advancement. From sorting vast datasets efficiently to optimizing complex decision-making processes, understanding algorithms is crucial for any programmer aiming to build scalable solutions. The power of algorithms lies not just in their complexity but in how effectively they solve problems. By mastering algorithm design principles, developers can create applications that are both performant and maintainable across diverse platforms. Fundamental concepts in algorithm analysis. An effective approach to studying algorithms begins by grasping fundamental analytical techniques. This involves evaluating time and space complexity using Big O notation, which provides standardized measures of efficiency. Understanding these metrics helps programmers make informed decisions when selecting between different implementation strategies. For example, choosing an optimal search algorithm might mean the difference between linear versus logarithmic performance gains. Big O analysis considers worst-case scenarios rather than average cases, ensuring robustness against unexpected input sizes. This perspective prepares developers for real-world challenges where inputs often exceed initial expectations. Space complexity focuses on memory requirements, which becomes increasingly critical as application scales grow larger. Efficient use of resources remains essential even in modern cloud-based environments. Time complexity measures how execution time increases with input size, typically expressed as O, N, O, log N, etc. Space complexity evaluates additional memory used during computation, excluding original input storage needs. These two dimensions provide complementary views that help balance computational speed against resource consumption constraints faced by software engineers daily. By applying these analyses consistently, developers gain deeper insight into algorithm behavior under varying conditions. This knowledge enables better trade-off assessments between different solution approaches. Sorting algorithms explained through Python examples. Bubble sort offers a simple introduction to comparative sorting methods. While its quadratic runtime makes it inefficient for large arrays, implementing it in Python demonstrates basic iteration patterns useful for learning purposes. A visualization would show elements gradually moving towards their correct positions through adjacent swaps. Let's examine sample code illustrating this concept. Def bubble underscore sort, arr n equals len, arr, for I in range, n swapped equals false for j in range, 0, ni1 if arr, j, arr, j plus 1, arr, j plus 1, equals arr, j plus 1, arr, j, swapped equals true if not swapped. Break return arr. This implementation includes an optimization that stops early if array becomes sorted before completing full passes. However, the best case remains O, n, while worst case stays at O, n superscript 2. Quicksort presents another classic divide and conquer strategy. Unlike bubble sort, it partitions arrays around pivot points recursively achieving average O, n log n. Performance, though worst case, can degrade significantly. Implementing quicksort in Python reveals interesting characteristics regarding recursion depth limits and partition selection choices affecting actual runtimes experienced by users. Merge sort follows similar asymptotic bounds as quicksort but guarantees consistent performance regardless of input order due to its stable merging process. Implementations demonstrate elegant recursive structures common in many functional languages. Each algorithm has distinct advantages depending upon context. Understanding these differences allows developers to select appropriate tools based on problem-specific constraints like available memory or required stability features. Searching techniques and their implementation details. Linear search serves as foundational technique for finding target values within unsorted collections. Its simplicity comes at cost of potentially scanning entire dataset unless early termination occurs. Binary search dramatically improves lookup speeds when dealing with sorted sequences. The algorithm works by repeatedly dividing search interval in half until desired element is located or determined absent. Here's an illustrative Python function demonstrating binary search logic. def binary underscore search, ARR, x low equals 0 high equals len, ARR, 1 while low. This implementation assumes array is already sorted ascendingly. If not, results become unpredictable and potentially incorrect. Both techniques highlight importance of preconditions in algorithm effectiveness. Proper preparation ensures intended behaviors manifest correctly without unexpected outcomes. Data structure considerations for optimal performance. Selecting appropriate data structures directly impacts algorithmic efficiency. Hash tables enable constant time lookups when properly implemented yet require careful management of collisions. Tree structures offer ordered traversal capabilities suitable for hierarchical data organization. Different tree implementations influence insertion/deletion complexities according to specific balancing mechanisms employed. Bloom filters exemplify probabilistic data structures handling membership queries with minimal memory footprint, although accepting potential false positives as inherent limitation. Picking right structure depends heavily on particular use case requirements. Real-world applications frequently combine multiple data types strategically for enhanced overall system functionality. Dynamically adaptive solutions using heuristic methods introduce approximations allowing faster computations, albeit sacrificing absolute accuracy. These approaches excel particularly well in domains requiring near-optimal solutions quickly. Genetic algorithms mimic natural evolution processes to explore solution spaces systematically. They apply mutation/crossover operations, iteratively improving population quality over generations. Ant colony optimization leverages swarm intelligence principles, observing ants' pheromone trail behaviors to solve combinatorial optimization problems effectively. Such heuristic paradigms find practical uses in logistics planning, network routing, and machine scheduling, among other areas needing efficient approximate answers rapidly. When designing systems involving dynamic environments, incorporating adaptive heuristics enhances responsiveness capabilities, enabling timely adjustments to changing conditions. Graph traversal strategies and pathfinding algorithms. Depth-first search explores graph nodes exhaustively, following single path until reaching dead ends, then backtracking. It's particularly suited for connectivity analysis tasks. Breadth-first search prioritizes exploration level by level from starting node outward. This method finds shortest paths in unweighted graphs efficiently by nature of layer-wise expansion. Dijkstra's algorithm extends BFS ideas to handle weighted edges, computing minimum distances between vertices effectively through greedy approach reinforced by priority queues. ** incorporates heuristic estimates alongside Dijkstra's framework, enhancing pathfinding capabilities, especially within grid-like environments commonly encountered in game development contexts. Each traversal method possesses unique strengths, making them applicable across various scenario types ranging from social network mapping to robotic navigation systems. Evaluating trade-offs between accuracy and efficiency. Algorithm selection often involves navigating trade-offs between precision levels achieved versus computational costs incurred. Exact algorithms guarantee accurate outputs but may exhibit slower performances. Approximation algorithms sacrifice some degree of accuracy to achieve significant improvements in processing times, becoming vital for NP-hard problems lacking polynomial time solutions. Monte Carlo methods employ randomness to estimate probabilities within acceptable error margins, offering viable alternatives where precise calculations prove computationally prohibitive. Choosing between deterministic versus stochastic approaches requires thorough consideration of domain specifics, including tolerance thresholds for imprecision and urgency demands imposed by operational timelines. Crafting custom algorithms for specialized problems. Creating bespoke algorithms tailored specifically to novel situations demands rigorous problem decomposition followed by systematic pattern recognition exercises. Identifying recurring subproblems forms cornerstone of successful custom algorithm creation. Reusable components accelerate development cycles while reducing maintenance overheads associated with redundant coding efforts. Optimization techniques such as memoization cache previously computed results, avoiding unnecessary recomputation whenever same inputs occur subsequently. Dynamic programming builds upon memoization concepts, organizing overlapping subproblem resolutions systematically according to bottom-up methodologies. Designing domain-specific solutions benefits greatly from leveraging existing theoretical foundations established within computer science literature. Practical tips for effective algorithm study begin with concrete examples. Translating abstract mathematical descriptions into tangible code representations facilitates conceptual understanding necessary for mastery. Solving LeetCode-style puzzles regularly reinforces core competencies, helping identify gaps needing further attention while building confidence through repeated practice sessions. Participate actively in online communities dedicated to algorithm discussions. Engaging peers exposes learners to alternative perspectives, broadening comprehension horizons beyond textbook limitations. Document personal progress. Tracking completed exercises categorically allows identification of strength/weakness areas warranting targeted improvement initiatives. Conclusion: algorithms remain indispensable tools empowering programmers to craft intelligent systems capable of tackling intricate challenges efficiently and elegantly. Through deliberate study combining theory with hands-on experimentation, developers can elevate their skills, continuously adapting new methodologies as technologies evolve relentlessly forward.